So if we want to know the average weight of a child at birth in the state of Uttar Pradesh. Okay, obviously the setup is not advanced enough for us to know the weight of every child which is born in the state of Uttar Pradesh. So what would we do? We'll just take a sample of weight of some kids for which data would be available. So, as is the practice, we'll use mu for population mean. So let mu denote. So we might have a situation may be available infants. I will denote these figures with small x when we have actual numbers. So the sample weight ये इतनी सी बात है. हाँ. So most of the data that we hear about, starting from GDP figures, inflation figures, literacy rate in a region or a country, information about availability of clean drinking water is all information drawn from samples. Okay, so when we read that literacy rate in India over a period of 30 years has increased from a particular figure to a particular figure, nobody is asking everyone in the country. Okay, so 30 years ago, we might have had a a sample based on which literacy rate for the country as a whole. That information was drawn. You can have a sample now, and again, literacy rate for the country as a whole. That information would be drawn. GDP, this exercise is conducted much more frequently. Inflation, even more frequently. We have information available about wholesale price index every week. This is the exercise that is done. Yeah. So we have a well-established theory around sampling and statistical inference. And we can imagine a few hiccups here and there would lead to a miscalculation of GDP, and that will have consequences. Similarly, for inflation, it's done so frequently. A few theoretical errors here and there would lead to a disaster because this information is also used for making policy. When discussing general concepts, and methods of inference, it's convenient to use standard notations. Is there a lot of disturbance from the background from my side?
No, sir.
Okay. And the established convention is to use the Greek letter theta. Now we come to point estimate. We also have next chapter is internal estimation. So point estimate of any parameter theta. Now this theta can be the mean of the population that we might want information on. It can be variance of the population. It can be population proportion. Statistic here is what type of calculation we're doing from the sample. Okay, this sentence is important. The selected statistic. So whenever we have an estimator, we just put a caret on top. Okay. Generic notation, if the generic notation is theta for a parameter, its estimator would have a caret on top. Okay, let's see an example. So what's happening here is a car manufacturer wants information on how reliable the new bumper that they developed is. The job of a bumper in a car is one, to save the rest of the car from damage. So the bumper is supposed to absorb the shock when there is an accident. And two, the bumper is also supposed to ensure that the minimum amount of damage is done if there's a human being or any living being on the other side. Okay, so the random variable is defined as the number of crashes. These are test crashes that result in no visible damage to the automobile. The aim is to estimate the proportion of all such crashes that result in no damage. So the automobile manufacturer is producing and selling. Now they want to figure out in all the crashes that will happen, what's the proportion of crashes that will result in no damage. Okay. So what they do is they conduct 25 trial crashes and they observe that the value of the random variable x is 15. So out of these 25 trial crashes, 15 of them are cases in which there's no visible damage to the automobile. Okay, so population parameter is denoted here by P. Estimator would be denoted by same symbol with a caret on top. Here, this is the sample proportion. which is the value of x from the sample divided by the sample size. Okay, now it's very important to use the correct words. When we have generic notation, and we've seen uppercase letters is generic notation. So whenever we have this uppercase X, okay, not figures, but generic notations, then we have a estimator. Okay. When we have a particular sample and we obtain a particular value, that is an estimate. Okay. Now, calling this an estimate would be wrong. Calling this an estimator would be wrong. Till here, things look simple. Again, let me write if for each okay, that's one of the issues that we have to deal with in estimation, and to bring out this problem, let's see the next example. Okay, now because it's a book for engineers primarily, they use engineering terms. Now I will change. They're using dielectric breakdown voltage. I have no idea what that means. We'll just change the term. So let's say we have 20 observations on height of dogs. Yeah, height is normally distributed for most living beings. So we have a data set. Let's see. These are centimeters. Okay, it तो fit नहीं हो रहा. Say a particular breed. These are pretty tall dogs. So these are feet. No, inches. So 24 inches, around 2 feet. Okay, 2.5 feet, which is fine. Now we know that population distribution of height of Saint Bernards is normal. with mean value denoted by mu. There'll be some mean value. Because normal distribution is symmetric. Mu is also median of the distribution. Okay, so immediately we have two candidates that we can use from sample data to estimate the mean value for the population. Is the sample mean and the sample median. So what we have is a random sample. We have these 20 figures. And this is a sample from normal distribution. Because the population of all, the height of all dogs is normally distributed. So you can calculate the following estimators. And also estimates for mu. So we have the first estimator, which is naturally the first contender. This is the sample mean. Okay, because the generic notation, I'm using uppercase X with a bar. A particular estimate will be denoted by smaller case X with a bar on top. Okay, the sample that we have sums up to this. So 27.793. This can be a particular estimate for the mean height for St. Bernards. But because we know in the population that mean will be equal to median, so we have another contender, which is the sample median, X with a tilde on top. Okay, because we have an even number of observations, the median would be the middle two value summed up divided by 2, which is 27.960. Okay, now we can be innovative beyond this. So we can use this estimator. The minimum value plus the maximum value divided by the 2. This is the average of two extreme values. Estimate here would be noted minimum of smaller case I, max of smaller case xi divided by 2. These are 24.46 plus 30.88. Okay, again, not far off from the two values that we already have, or we can just take trimmed mean as an estimator. X bar trim 10, just 10% trimmed mean. which means we take out 10% of the largest values out and 10% of the smallest value out. 10% of this sample, which has 20 observations, would mean taking out two largest and two smallest values. So the estimate would be total of all observations minus two smallest divided by a smaller number, now 16. Okay, we again have keep all the values around 27. Now each of these can be possibly used for drawing out information about the population mean. Which of them is the closest to the true value? That we do not know. We would not know unless we know the true value. I have to write these sentences because I don't even have half the people in the class to make this document useful later on. Okay, if we stop at this point, then this would not be a very interesting theory to study. Okay, so we can answer a slightly different question. The question Okay, so for a particular sample, we would not know which of the estimates that we have obtained, these four values, is closest. But what we can know from the theory of statistical inference is in repeated sampling, which of these will give and which is expected to give an estimate closest to the true value. Okay. So this is the question that we will attempt to answer in the theory.